Welcome to today's class. I'm glad to have you here. Remember, in our last class, we discussed about calorimeter. And today, I want us to continue with calorimeter. Now, this is a calorimeter. A calorimeter, like we said at that time, is a device for measuring quantity of heat energy. Now, this is a typical calorimeter. Now, a typical calorimeter has a hole to take the thermometer. This is the thermometer. Now, this is the stirrer. Now, if we open it, we can have the stirrer. We have the thermometer there, and this is the main calorimeter. Why this is a container? Now, the container, inside this container has an insulator. The insulator is for protecting heat so that there won't be heat transfer from this can to the container. Now place it back. And today I want us to look at a situation where we heat a metal elsewhere, maybe in a heating chamber. After heating it, then we transfer it in a calorimeter. Now, assuming the calorimeter has some quantity of water. Now, if we have some quantity of water in this calorimeter, now we heat the metal. After heating the metal, now this is a pair of tongs. Now this pair of tongs, we use it to hold this metal. After heating it, we transfer it into this calorimeter and then cover. Once we cover, to avoid the heat losses, now we stir. This is how we stir. And now this thermometer will record the heat, the temperature of the water. Now, inside this, we have the solid, we have the water, and then we have the container. Now, remember, we have the calorimeter, we have the solids, and then we have water. So these are the three things I want us to look at. Now, a solid was heated elsewhere, transferred into a calorimeter containing water. So we're going to look at these three things. Now, the hot solids will lose heat. That means heat loss by solid, is equal to, now, heat gain by the calorimeter. Heat gain by calorimeter plus, already there is water inside that can. Now plus water there. In other words, we can now bring in our formula. Remember, our formula is quantity of heat is equal to mc delta theta, which will give us maybe mass of the solid, specific heat capacity, and then heat stream. Now we now have heat loss by solid will give us mc delta theta is equal to heat gain by the calorimeter, mc delta theta 2 also plus that of water, quantity of heat gained by water also will have mc delta theta. Now we can now bring in our various terms. This is our solid. It can be copper, it can be aluminum, it can be anything. So assuming we have this, we can now have mass of the solid, which is that metal we have, specific capacity of solid. Now we can erase this and have our here temperature of the solids minus, and of course by the time you bring the two together, we'll have a final temperature. Final temperature of the mixture is equal to, now this is the calorimeter, we can subscript it to the C. Mass of calorimeter, specific heat capacity of calorimeter. Now we can click this, and of course what we now have here is water and the solids. So we can now take final temperature minus initial temperature. So this is for the calorimeter plus that of water. Now water will now give us, we have as usual mass of water, we substitute it with W, specific heat capacity of water, and final temperature now, because we now have water, and of course that water has also initial temperature. So we can now have minus initial temperature. So this is our formula. Now we can now work this is out, where MS is mass of the solid, CS specific heat capacity of the solid, theta X the temperature of that solid. Now this theta F is the final temperature of the mixture. Now MC, mass of mass of the calorimeter, specific heat capacity of calorimeter, theta F, final temperature of the mixture minus initial temperature of the water. Plus this one. And of course, because the two of them are together, that is why we are using this temperature, these two temperatures here. This one is separate. Mass of water, specific heat capacity of water, and we have final temperature minus initial temperature. Now we take calculation here. Okay. Example 1. A piece of copper of mass 0.1 kg is heated to 100 degrees Celsius and then transferred to a well-lagged copper can of mass 0.05 kg containing 0.2 kg of water at 10 degrees Celsius. Calculate the final temperature of the mixture. Here we are given the specific heat capacity of water 4,200 joules per kg per Kelvin. Now specific heat capacity of copper is 400 joules per kg per Kelvin. Now we revert back to our former calorimeter. Now in this this is a calorimeter containing water. Another mass, a mass is heated elsewhere up to 100 degrees Celsius and then quickly transferred into this calorimeter cover and then is there. Remember, it's well lagged. It's well lagged. Now this cover is to enable heat not to escape to the surroundings. Okay. Now solution. We have copper. Now, because this material is copper, the calorimeter also is copper. They will share the same SI unit. Now, sorry, the same specific heat capacity. Now we have mass of solid, MS. Mass of solid is 0.1 kg. We now move to the temperature of solid now, which is given as 100 degrees Celsius. Transfer into a well-lagged copper calorimeter. Now, mass of calorimeter 0.05 kg. Now, mass of water is 0.2 Now, initial temperature of water now, initial temperature, theta I, is 10 degrees Celsius. And we are looking for the final temperature. So we can now say, let the final temperature be theta F. Now, we are given that the specific heat capacity for water is 4,200 and specific heat capacity for copper is 400 joule per kg per Kelvin. Now, we employ our formula. The first one, losing heat. The copper will lose it, which is solid, mass of solid, specific heat capacity of solid. Now, temperature of solid minus the final temperature of the mixture is equal to mass of calorimeter first. Mass of calorimeter times specific heat capacity of calorimeter. Now, temperature change. Final minus initial. Plus that of water. Mass of water, specific heat capacity of water, and temperature change, which is theta F minus theta initial. Now we substitute. Mass of solid from what you have there, which is 0.1, times specific heat capacity of solid. Because it is a copper solid, we use the heat capacity, specific heat capacity of solid, which is 400, times the temperature of the solid, which is 100, minus the final temperature, theta F, equals mass of the calorimeter is 0.05 times specific heat capacity. Because this capacity is, let's say, transferred to a well-known copper can of mass. So, because the calorimeter is copper, we use specific heat capacity of copper, 400 into theta F minus initial temperature. The initial temperature is 10 degrees Celsius plus mass of water. Mass of water from what we have is 0.2 times the specific heat capacity. See, the specific heat capacity of water is given to be 4,200 into theta F now, the unknown, minus 10, which will give us, now if we multiply out everything, we have 0.1 times 400. By calculation, we have that 0.1 times 400 is 40 into, you bring this one, 100 minus theta F, which is equal to 0.05 times 400. By calculation, it will give us 20 into theta F minus 10 plus 0.2 times 4,200. By calculation, it will give us 840 into theta F minus 10. At this point, we expand the bracket. Now, 400 times, 40 times 100 will give us 4,000 minus 40 times theta F will give us 40 theta F, which is equal to 20 times theta F, 20 theta F minus 20 times 10, which will give us 200 plus 840 times theta F, 840 theta F minus 840 times 10, which will give us 8,400. At this point, we collect like times. 4,000 is already here. We drop it there. 4,000. Now, this one minus, if it crosses over, it changes to plus. Which other one? This one also minus. If it crosses over, it changes over to plus 4,800, which is equal to, this one is already here. You leave it there, theta 20 theta F. This one is here, plus 840 theta F. Now the one remaining is this one. It will cross over to become 40 theta F. Now, the whole of this, if we add 4,000 plus 200 plus 8,400, by calculation, we will have 12,600. This is equal to 20 theta F plus 840 plus 40 will give us 900 theta F. Now, making theta F the subject, theta F will give us 12,600 all over 900. Now, 0 cancelling 0. 126 divided by 9. By calculation, we have 14 degrees. Therefore, the final temperature of the mixture of copper heated elsewhere up to 100 degrees Celsius and transferred quickly into a copper-lagged calorimeter containing that quantity of water. Now, the final temperature of the mixture, theta F, will give us 14 degrees Celsius. Okay, this is the final answer. Okay, example 2. A piece of copper metal, 200 grams, is removed from a furnace at the temperature of theta degrees Celsius and quickly dropped into a copper vessel of mass 10 grams containing 100 grams of water. Containing water. If the initial temperature of water is 30 degrees Celsius and the final temperature is 70 degrees Celsius, find the value of theta. Now we have the specific heat capacity of copper to be 420 and that of water to be 4,200. Now the first thing we do is to bring out the parameters given. Mass of piece of copper of mass, that means the solid there. Mass of solid here is 200 grams. Now because this one is in grams, this one is in kg, we convert this to kg, which will give us 0.2 kg. Now, let's move from the phone and from the temperature. Now, temperature theta S, temperature of the solid here is theta. Mass of the calorimeter is 10 grams. And of course, if you convert 10 grams to kg, we'll have 0.01 kg. Mass of water. Mass of water is 100 grams. 100 grams will give us 0.1 kg. Initial temperature of water, theta I, is 30 degrees Celsius, while theta F is the final temperature now is 70 degrees Celsius. Then we have to calculate this. Okay, so we have mass of solid, specific capacity of solid, temperature of solid minus the final temperature is equal to mass of calorimeter, specific capacity of the calorimeter, the final temperature of the mixture minus initial temperature, plus for the water, we have mass of water, specific capacity of water, and the final temperature of the mixture, and that of initial. So, if we bring in all this, we have 0.2 times specific capacity of solid. Now, this is a copper solid. Now, the specific capacity is given to be 420 into, and of course, we are looking for theta S, and it's given to be theta minus the final temperature. Final temperature 70, which is equal to mass of the calorimeter. Mass of the calorimeter is given as 0.01 into specific heat capacity, because this is a copper vessel too. So we use 420 times the final temperature, which is 70 minus 30, plus that of water. Mass of water is 0.1 times specific capacity of water 4,200 times the temperature change 70 minus 30. Now, by calculation, 0.2 times 420 will give us 84. So we now have 84 here. 84 into theta minus 70 is equal to 0.01 times 420. By calculation, it will give us 4.2. 4.2 into 70 minus 30 will give us 40 plus 0.1 times 4,200. By calculation, it will give us 420 into 70 minus 30 will give us 40. Now we open this bracket. It will now have 84 theta minus 84 times 400. So 84 times 70 will give us 5880, which is equal to 4.2 times 40 will give us 168 plus 420 times 8 times 40 will give us 16,800. Now at this point we collect like terms. 84 theta is equal to 168 is already there. 168 plus 16,800. Now this one crossing over will give us plus 5,880. Now 84 theta will give us 168 plus 16,800 plus 5,880. Everything will give us 22,848. 22,848. Now, making theta the subject, we'll have 22,848 divided by 84. Therefore, the final temperature of the mixture will give us 272 degrees Celsius. Of course, it's a very high temperature. Okay. Now, this is where we'll take it. Alright. This is where we'll draw the lesson to an end for today. Please remember to subscribe so that once we upload new lessons, you will get notifications. Thank you very much.